Hi, Ivan folks. Okay, welcome back to Subspace Mechanics. Today we're just going to look at the electromagnetic field and some basic constraints, well, not really constraints, but motivations that are going to, things that are going to motivate our building of a subspace mechanics. And of course, when we build the subspace mechanics, our goal is to have a model that reproduces the real fields, the real world, and the electromagnetic fields are, of course, crucial here. So let's take a close look at some historical efforts to do exactly what we're talking about here. My apologies for the chicken scratches here. Of course, electromagnetism is what we're after. We want to go from a subspace distribution of some phase-space variables to our fields. In this case, we're just going to look at E and B. We're going to consider very simple fluid-like models, which can reproduce our electric and magnetic fields. So let's do a little reminder. Maxwell's equations. Divergence of the electric field is equal to the charge density. We're going to use SI units here, and we're going to use this, what do they call that, differential notation. Of course, this is identical to the integral notation, which was more fashionable and perhaps easier to understand. You have a closed surface around any closed surface, the integral of the electric field over that surface, where S is the normal to the surface, is going to be equal to the total charge enclosed. And so what does this tell us? It tells us that the charge density acts like a source in some way similar to any other source phenomenon. If you have, for example, a speaker, the total sound energy over any going outwards over any closed sphere around that speaker will be equal to the energy coming out of the speaker. Pretty simple. Of course, this also leads to Coulomb's law, 1 over r squared force. We have that the divergence of a magnetic field is 0. There are no magnetic monopoles. This also suggests right away that we could write magnetic field as a curl of some magnetic vector potential. We have that the curl of the electric field is equal to a rate of change of the magnetic field, and we have the curl of magnetic field being equal to source term from a current and a term from the change of the electric field. Now, in terms of this source term of the current, you might be able to visualize this a little bit in a subspace model. If you have a wire, let's say, and some current, and if we're moving through some sort of subspace system here, you might expect that there be some motion close to the current, and this would decrease as you go further away. And this, of course, is an area where the field has a net vorticity. Even if its individual particles are not oscillating as such, the vorticity here is non-zero. So we see that magnetic field sort of behaves like a vorticity. Remember that the vorticity in a fluid is the curl of the fluid velocity, the bulk fluid velocity, which I'm calling U here. And we have a similar, a useful potential where we often write the, sorry, not the charge density, a potential, electric potential, voltage, defined such that the gradient of the potential is the electric field. And you actually occasionally need a dAdt term here if you're not in a static regime. But the point is that we have this term here which acts something like a pressure. Remember that in a fluid, a gradient of the pressure gives you a force term. These are the fluid analogies which we're looking at here to motivate our subspace mechanics. Now, and remember that subspace mechanics, there's never only a single model. We can always make more complicated models which also produce the same fields. But we want to start with a simple one that reproduces some elements of the fields so that then we can continue, build on it, and reproduce all the fields that we want with our subspace mechanics. So let's look at a couple other analogies. We have something called the Lorentz gauge condition, which is that the divergence of the magnetic vector potential plus 1 over c squared times the time derivative of the electric potential cancels out to 0. And we have a continuity equation for fluids which just is a very simple idea. It says that the rate of change of a density of a fluid, which I'll call n, is solely due to incoming fluid into the system. So this would be a divergence of the bulk velocity. And you can see that these two terms mirror each other. And we see again that the magnetic vector potential acts kind of like a fluid velocity, and that the potential is like a density or a pressure, really. And there's further coincidences, let's say, that might inspire us. We have a vorticity transport equation in fluids. That the vorticity in a fluid, the amount of rotation going on, is equal to a curl of our velocity of the fluid crossed with vorticity. And this is also mirrored in our magnetic field evolution for a plasma, where, again, as you might expect, this is a magnetic field here. This continues. Got some other examples. Field diffusion equations in vorticity. Vorticity can diffuse, diffusion constant, Laplacian. This is a classic diffusion equation. And we also have a magnetic diffusivity, which follows the same form. Surprise, surprise. So another constant here. That's embarrassing. What letter is that? I think it's supposed to be an eta. Now, I'm not going to go into too many details as we're just motivating here based on analogies of simple fluids. Now, we haven't even introduced spinning elements into our fluid yet, and we're already reproducing a lot of electromagnetism. And of course, in future episodes, we're going to try to get much more precise about what models for our distribution function allow for this analogy to work. In particular, we want to build a model of charges as vortexes, and they are cyclonic, if you will, or rotational. They have cyclonic and anticyclonic possibilities, such as antimatter and matter, which have opposite charges. Charges indicate the pressure difference. The pressure here is not a pressure of air, but a pressure of subspace constituents. And let's scroll down. We're going to have something. If we have a very simple model of space-time, we say that a distribution of gyrons or subspace constituents is simply a position velocity in subspace. Then we can define our electric field tension, our electric potential is going to be something along the lines of v squared f. So what I mean by this is an integral over all velocity space of, now what is this capital V is u minus v. And now this is not a gas velocity, this is our subspace particle bulk speed, which again is not observable in real space, but we're hypothesizing its existence in order to create a model to reproduce our fields. And this is called the peculiar velocity, the amount that a given particle is differing from the bulk velocity. And so this will be a candidate, if you will, for a simple model. Of course, we also have a magnetic vector potential, which will be given as the bulk flow of these gyrons, which is just getting used to this notation now. We're simply averaging over the velocity of the particles. And this one you might want to, there is a tempting to make a normalization factor here. We're not going to be very rigorous with our determination of units for this particular lesson, because I'm just giving the rough outline of why we need to consider such a fluid model. And before we get into modifications of it, which we need to have to exactly match electromagnetism, rather than with this hand-waving argument which you're seeing today. And many of you have seen these before. Once again, this stuff is over a century old. Lorentz was playing with these equations, many others. And once you have made these associations, then you can create a Vlasov equation sorry. Well, let's leave a collision term in here. Let's say it's collisionless for now, and it's zero. And in this Vlasov equation enables us to write the transport equation and to determine the evolution of our distribution, which then allows us to determine the evolution of our fields, hence giving us a good model of fields based on subspace mechanics. And there are even more nice fluid analogies, which I've left out here. But hopefully as we get more specific in terms of our definitions here and our units, we can return and look at all of the details here. We have the diffusion matchup. We have the vorticity transport matchup. The Lorentz gauge being almost equal to the continuity equation is really something. And this should really let you know something about electromagnetism. The exact format here for example, of this equation is not intuitive exactly what this implies about the fluid, but the fact that you have a changing vorticity leading to a force that part is a little bit intuitive, especially if you keep in mind that the force is a gradient in pressure. And we're going to try to keep these videos short, so the takeaway here is simply that electromagnetic forces have fluid analogs. And of course, this is also true for quantum mechanics, has fluid analogies, and also for general relativity, which has fluid analogies, some of which are, in fact, can be made experimentally. There's experimental analogs of general relativity is a very interesting field. And of course, the electromagnetic fluid is quite different from fluids that we know and love and drink. It's remarkably linear over 20 orders of magnitude in frequency space. For example, we don't see any kind of compressive wave. Typically we see the transverse radiation, which we know and love as electromagnetic radiation. So we'll get to those details in a later lecture. So thanks for tuning in.